Hi, and welcome back to another LeetCode problem. We're looking at LeetCode number 19, remove the nth node from the end of a list. It's a medium problem, and it has to do with list manipulation. So yeah, let's have a quick look at it. We're going to use our systematic approach, read the problem, check out the constraints, check out the examples, try to come up with a solution, and run time as well as space complexity before we write a single line of code. And then implement the solution that we came up with in code, and hopefully everything will work out without any hiccups. So let's dive into it. We are given the head of a linked list, and we are supposed to remove the nth node from the end of the list and return its head. Interesting. So the number of nodes in the list, so we have at least one node. That's good to know. And the values of the nodes are well, between 0 and 100. And the value of n will be between 1 and the length of the list. So SZ is the length of the list. Okay, so all right. So that means it is guaranteed that the node that we're supposed to remove exists in the list. That's what that means. Let's have a look at the examples. So here we have a linked list, 1, 2, 3, 4, 5, and n is 2. So we need to remove not the first, but the second element from the end. Okay, and then the resulting list is where we remove that element. Nice. Okay, here we have a list that only consists of one element, and we should remove the first element from the end, which is of course that only element, and then we return an empty list. So we should return none, I suppose. Here's another example where we should remove the last element, so the first from the end. That's the last one. So that means that it's not index-based when we count from the last, right? Removing the first means remove actually the last. And then we return the rest of the list, which is only the head without the tail that we removed. Okay, cool. So, well, since we're dealing with a linked list and we only have a handle to the head of the list, why is the value n? Is that the length of the list? No, oh no, sorry. Yeah, that's the nth node. Never mind. So something that we could do is we could just determine the length of the list. That would be an O of n operation. Then we just subtract whatever n we get from that. And then we do a second pass through the list and identify that element and just unlink it from the list. I think that's what we should do. So we will formulate this problem as remove the kth element from the beginning. But to determine k, we first have to determine the length of the list. So I think I'm going to write a little helper function here. Oh wait, before we write code, let's do a runtime analysis. So that will be O of n time and O of 1 space, which should be optimal. Yes, and so first thing is we're going to get the length of a list, right? And we just pass in a node. In the beginning, the length is 0. And whatever the length is, we're going to return it. And now we do while node length. We increase the length and we say node is node.next. So we just iterate through the linked list and determine the length. So length of our list is going to be get length head. Right. And now the k that we want to determine, that is equal to length minus n. But I think we have an off by 1 error. So let's just test. So if we pass this list in, we will have 1, 2, 3, 4, 5. So we'll actually get 5 back. But if we subtract the 2, that means k will be 3. So when we do the next iteration through the list, to stop at the third element, we would have 1, 2, 3. Oh, this is perfect because we have a pointer to the next, right? So that is perfect because we have a pointer to the next one. So we could say 3.next is none, and or we say 3.next points into the 5. So we could do that. But we have to be a little bit careful about edge cases. So this approach would work if n is not the same as the length. And we can have that n is equal to the length of the list. So what if n is actually 5, right? So then we would have to remove this element, the 0. Well, we could treat it as an edge case and just say if k is 0, that means we have to return head.next. And then we've removed the first element. We could do that. So that would also work. If, let's say, our n is 4, then our k would be 1. That means we visit one node, and then we know that we need to splice out the next. Okay, yeah, I think that should work. So the next helper function that we need is maybe remove. Def remove nth from start, and then we just pass in the node and k. Remove kth from start. Right, and then here we call that. And we're going to return. Are we going to return it? No, we're just going to call it. So we're going to call remove kth from start. We pass in the head again, and we're going to pass in our k. And if k is equal to 0, return head.next. That's our little edge case. Right. And if we, and otherwise we just, let me think. Yeah, I think that would work. That's probably a more elegant way of how to write this, right? Maybe like so, else we do that and then return head. Yeah, something like that. Okay, so now let's concentrate on where the meat is. So the previous node and the current node are none and node, right? Well, actually, we don't have to keep track of the previous one. But what we will do is while k, we do k equals k minus 1. And we say node is node.next. I think we might have to correct our k here. Well, let's see. So in our example, if k is 1, right? While k is larger than 1, we're going to reduce it. But if k is already 1, that means node is the node after which the 1 comes that we need to remove. Yes, I think that's how we should do it. So now we need to remove the node.next. So node.next equals, well, depends, right? Well, we know that the node that we're going to remove exists. So we know that node.next must exist, and it might have a successor or it might have a non-successor. But that's pretty much it. So we just change the pointer to the node that we want to move to its successor. And that should be it. Yes, I think that should be it. But I should probably check one more time if everything is correct. Let's just check one more time. Maybe we try this edge case. So we have one node and we're removing that one node. So we get the length. The length is 1. We determine our k. Length is 1 minus 1 is 0. So we run to this thing. So we have to say head is equal to the successor of head, which is none. The head will be none and then return none, which is perfect. That's exactly what we want. Let's look at the other case. So head points at a list that has element 1 and 2. The length will be 2. We reduce it by 1. So k will be 1. So this case does not catch, but this one does. So we pass in the head of the list and the value 1 for k. if k is larger than 1, well, k is 1. So the while loop does not catch. But what now happens is we say the successor of head is equal to the successor of the successor of head. So head.next is not 2, but head.next is going to be none. So we return a list that has just the head, which is perfectly fine. Cool. Okay, I think I've got some confidence now that this should work. Let's try it out. And it passes the test cases. Let's see if LeetCode accepts this submission. Yeah, so there you go. Yeah, there's also another way you could approach this, where you use a recursive approach, but then you immediately, every recursive call adds to your space complexity, right? Because it goes onto the call stack, even though you don't use an explicit data structure in your code. Recursion is like using a stack when you use recursion. So you definitely won't get O of 1 space, but you could do it in one pass that way. Because as you unwind your stack, you could reduce your k until it's 0, then you've reached a node that you need to remove. So, but this way you need 2 pass to determine the length, to calculate the position, and then remove that element from that position. That concludes this video.